For the capillary rise in soils, so the continuous void spaces in soil can behave as bundles of capillary tubes of variable cross-section. Because of surface tension force, water may rise above the phreatic surface. The height of rise of water in the capillary tube can be given by summing the forces in the vertical direction. So, if you can recall in your physics subject that um, we have there for fluids, topics for fluids, where it is discussed there if we have a fluid here or any any fluid like water, when you put a tube right here. So because of surface tension, there can be there can be a rise of the surface inside that tube. So that's what you call capillary rise of water. Now, the same way with soils. So if let's say this is the soil layer right here, then you have the water table in between that soil layer. This is the water table. And above that water table, there are void spaces on that soil. So that void spaces can act as capillary tubes or a tube right here where the water can seep through those spaces, straight through those spaces. So therefore, there can be a rise of, or there can be a layer in that soil that can be partially, or it can also be fully saturated with water. So uh, going back to the formula for the capillary rise, um, if we have a given tube that is uh, inserted or that is placed on the water, so that equivalent height can be computed using this equation right here. But of course, this is not applicable for soils because they are not tubes, but we will consider the pore spaces or the void spaces on the soil. So uh, again, that capillary rise causes negative pore water pressure on the soil because there is a suction effect on the water above the surface of this water inside the tube. Now, as you can see in this figure, we have here the capillary action of water on the tube. So it has the same behavior on the soil. Now, as you can see here on letter B, this is the equivalent diagram for the pore water pressure for the water from the surface. So above the water surface at a certain height within the capillary rise, so we have an equivalent negative pressure or equivalent negative pore water pressure. It's just the height times the unit weight of water, or simply the height is measured from the free water surface to the point where we will determine that equivalent for water pressure. So to determine the capillary rise of water in the soil, we'll just use this formula where capillary rise in millimeter is equals to C, or the constant, which varies from 10 to 50 mm square, divided by the product of void ratio and the effective size, which is also in millimeter. So these are the approximate range of capillary rise in soils depending on the type of soil. So compute the equivalent pore pressure at any point, or at any point in a layer of soil partially saturated caused by the capillary action. So again, it is a negative pressure. So U is equals to negative S, which is the degree of saturation of the soil divided by 100, then multiplied by unit weight of water times H. For the sample problem, we have here a dense silt with the following properties. We have a void ratio of 0.4, specific gravity of 2.7, effective diameter of 10 micrometer, and a constant of 0.2 square centimeters. Said here that the free groundwater level is 8 meters below the ground surface. So let me just draw. 8 meters is around right here. Okay. So this is the groundwater level right here. That's 8 meters. Okay. So the first required is what will be the height of capillary rise in the silt. So if this is your water level, well, the water table, so there will be capillary action. What will be the equivalent height of that capillary action that takes place here on this soil? Then number two, find the vertical effective stress in kilopascal at 5 meters depth. So from the ground surface, we will measure 5 meters. So 2, 3, 4, 5, let's say right here, let's say that's point A. We will determine the vertical effective stress in kilopascal. So this is 5 meters. Okay, this is 5 meters. So we said here that we assume that the soil above the capillary action to be dry soil, while the soil that is within the capillary action should be partially saturated at 50%. So of course, the soil below the water level is fully saturated. So number three, at 10-meter depth, assume that the soil, we will determine the effective stress. So assume the same, that the dry soil is above the capillary action, and within the capillary action, it is partially saturated at 50%. So 10-meter depth, it's right here, 10 meters. So let's say that's point B. Okay, so this is 10 meters. So first, let's determine the height of capillary rise in the silt. So the formula is H is equals to C over E T 10. So looking at the units, for the constant, we have square centimeters. For the effective diameter, we have 10 micrometer. So if we want to have a centimeter value for the height of capillary rise, so we have to be consistent in using the unit. So both the effective diameter and capillary constant should be in centimeters, or if we want that in millimeter, so this should be in square millimeter, and this one, the effective diameter, should be in millimeter also. So but here let's just convert it into centimeters, so that we will not convert the capillary constant into square millimeter. So we'll just use centimeter unit. So now, what will be the conversion factor for 10 micrometer into mm? So let's convert this. 1 micrometer is equivalent to 1 times 10 raised to negative 6 meters. Then 1 meter, we convert it to centimeter, that's 100 centimeters. So these are the conversion factors. So if we're gonna convert this 10 micrometer here, so just multiply 1 micrometer. So the numerator, we have 1 times 10 raised to negative 6 meters. So from meter to centimeter, just multiply 100 centimeters over 1 meter. So that these units will be cancelled out. Computing that, we have 10 times 1 times 10 raised to negative 6 times 100. That's 0.001 centimeters. So we all now have centimeter unit. So we can now compute the height of capillary action. So C is 0.20 square centimeters to be divided by E 0.4 and T10 effective diameter 0.001. So 0.001 centimeters. So centimeter will be cancelled out. We only have centimeters. So the capillary action is in centimeters. Okay. 0.2 over 0.4 times 0.001. That's 500 centimeters. Or in meter, 500 centimeters just divided by 100 using this conversion factor, the height will be this is 5 meters. 500 centimeters is equivalent to 5 meters. So that's your answer in number 1. Means that the capillary action, so the maximum height that the capillary action reach is 5 meters above the water level or the water table. So let's draw another line for the capillary action. So 5 units above or 5 meters above the water table. So we have 1, 2, 3, 4, 5 right here. Okay. So that's your capillary action. 5 meters. Okay. For number 2, we'll now determine the effective stress at point A. But since we don't have yet the unit weight for each layer of the soil, so we have to determine first the equivalent unit weight. So since they are of the same type of soil, which is dense silt, so their void ratio and specific gravity are the same. They will only differ in their moisture content as well as the degree of saturation. So let's rewrite the given void ratio and specific gravity for each layer. So we have E here 0.4 and G 2.7. So it is the same for this partially saturated layer due to capillary action. So 0.4, G 2.7, E 0.4, G 2.7. So said there that assume that the layer above the capillary action will be dry soil. So we will determine the dry unit weight. For the partially saturated or the layer within the capillary action, it is partially saturated at 50%. Now, the portion where it is submerged below the water level, the degree of saturation is 100. So it is fully saturated because it is submerged. So here, let's say the unit weight here is moist or partially saturated, or I can write moist soil, or here this is fully saturated, so gamma sat. So for A first, So let's determine the stresses present at point A. So from the given degree of saturation for dry, the degree of saturation for that is 0. So that's 0. Now, how to determine the dry unit weight, moist unit weight, and saturated unit weight of the soil? So we have a general formula in your soil mechanics. If we have a given specific gravity and void ratio, we can use this general solution for the unit weight. So we have specific gravity plus SE over 1 plus E multiplied by the unit weight of water. For dry unit weight, uh, the degree of saturation is 0. So 0 times E, this term will be cancelled out. So the dry unit weight is equals to G over 1 plus E, unit weight of water. So for the moist unit weight, we have given degree of saturation, so we can just easily use this general solution for the unit weight. For the saturated unit weight, the degree of saturation is 100%, so S will be 1. So S is 1. We can write it as G plus E over 1 plus E multiplied by the unit weight of water. So we can now solve the dry unit weight. So the dry unit weight is 2.7 over 1 plus 0.4. So 2.7 over 1 plus 0.4. Sorry, I have to include the unit weight of water, which is 9.81 kilonewtons per cubic meter. Okay, so times 9.81, that's 18.919 kilonewtons per cubic meter. Next, for the moist soil, we have 2.7 plus, so it is partially saturated here, which is 50%. So in decimal, that's 0.5 times E 0.4 over 1 plus 0.4 times 9.81 kilonewtons per cubic meters. So that is equals to, just continue this, plus 0.5 times 0.4, 20.321 kilonewtons per cubic meter. Okay, next, for the saturated soil, we have G plus E, so 0.4 over 1 plus 0.4 times 9.81 kilonewtons per cubic meter. So that's 21. Okay, let me replace this by 2.7. 2.7. 21.722 kilonewtons per cubic meter. Okay, so let's rewrite those values. Here, the figure, we have 18.919 kilonewtons per cubic meter. The moist is 20.321 kilonewtons per cubic meter. And for the saturated, we have 21.722 kilonewtons per cubic meter. Okay, so we can now solve the stress at point A. So for number 2, since the required only here is the effective stress, we can solve that using this solution. So the general solution, we have the total stress is effective stress plus the pore water pressure. Or we can rewrite that by determining the vertical effective stress is just the difference of the total stress minus the pore water pressure. So let's solve the total stress first. For the total stress, so at point A, it's right here. So we have two layers for to be considered in determining the total stress. We have the dry layer, the soil layer, and this layer right here, which is partially saturated due to capillary action. Okay, so it's the capillary action. So said there that is 5 meters below the ground surface. So it means that if this is 8 and the capillary action is 5, so the remaining height here is 3 meters. So if we have a total depth of 5 meters from the surface to point A, so the remaining depth here is 2 meters. So we consider 2 meters of partially saturated and 3 meters of dry soil. So for the total stress at A, so just add the product of the unit weight and the height. So let me rewrite that. Dry unit weight times 3 meters plus the unit weight here multiplied by 2. The moist times 2 meters. Okay, that's how you solve the total stress. So 18.919 kilonewtons per cubic meter times 3 meters plus the moist 20.321 kilonewtons per cubic meter multiplied by 2 meters. Okay, so 18.919 multiplied by 3 plus 20.321 times 2. So that's 97. That's total stress, 97.399. That's in kilopascal because we have a unit of kilonewton per square meter. Okay, so that's the total stress at A. Number 2, the second is the pore water pressure. So we have here a capillary action. So this is also affected by the pore water pressure if we are to determine the pressure at any point within the capillary action. So in the capillary action, we have solution in determining the pore water pressure, which is negative S for the degree of saturation on that layer over 100 times unit weight of water times the height. So what's the height here? That height is measured from the water table to the point where we will determine the pressure. So we have here point A. It means that the height there is from this water table to point A. So this vertical distance here, that will be the height that you will use. So what's the height here? So if this is 5 meters and this is 2 meters, what remains is this vertical distance, which is 3 meters. So it means the H is 3 meters. The distance from water surface or water level to point A. Okay. So H is 3 meters. So U is equals to negative degree of saturation of the capillary action, 50 over 100. So here, as here, we will input the percent value, not the decimal value. So 50. Or you can just simply replace this by the decimal value of the degree of saturation. Just write 0.5. So times 9.81 kilonewtons per cubic meter multiplied by H. So H is 3 meters. So U is equals to negative negative. So 50 over 100 is 0.5 times 9.81 times 3. So that's in kilopascal again. That's negative 14.715 kilopascal. Okay, that's your pore water pressure. And we can now determine the effective stress at point A by subtracting the total stress and the pore water pressure. So 97.399 kilopascal minus negative 14.715. So negative, they will become positive. So that's in kilopascal. So we will just add the two instead of adding, instead of subtracting the two values. Since they are both negative, we'll just add that 14.715. Okay, we have 112.114 kilopascal of effective stress at point A. So these are your answers. But since what is only required is the effective stress at point A, this is your final answer. For number 3, okay, for number 3, 10 meters depth. So this is point P. It means that if you have 8 meters here, we have an additional 2 meters, but it is below the water level. So this is 2 meters right here. So point B. So let me write it here. For number 3, we can now determine the total stress, which is equals to effective stress plus U. Or if we determine the effective stress, total stress minus U. So this is the easier solution. We determine separately the total stress and the pore pressure. So for the total stress, just add all the product of unit weight and its corresponding depth for each layer. So we have here 3 layers: the dry layer, the moist layer, and this fully saturated layer, which is 2 meters below the water table. So let's write that. The dry unit weight multiplied by 3 plus the moist unit weight multiplied by total depth of this one is 5. That's 5 meters plus the saturated multiplied by 2. Okay, let's rewrite that. 18.919 kilonewtons per cubic meter times 3 plus the moist 20.321 kilonewtons per cubic meter times 5 plus saturated 21.722 kilonewtons per cubic meter times 2. So the answer is times 3, 20.321 times 5, 21.722 times 2. That's 201.806. 806 kilopascal. That's your total stress at point C. Point B, rather. Okay. So for the pore water pressure, so our location is submerged. So the pore water pressure there is just the product of the unit weight and the height. Okay, so here, since the point where we will determine the pore water pressure is which is at point P, we will just measure again the height from the water table to the point where we will determine the pore pressure. So from the water table to point B vertically, that's 2 meters. So it means we have 9.81 kilonewtons per cubic meter, and we have 2 meters. Okay, so unlike on number 2 question, the point where we determine the pore pressure is within the capillary action, it is not submerged. So since it is within the capillary action, the corresponding solution for that is this negative pore pressure solution. Okay, but if it is submerged, so the point where we will determine the pore pressure, if it is submerged, that's positive, and it is just the product of unit weight of water and H. Okay, so 9.81 times 2 is 19.62 kilopascal. So for the effective stress, so this is at point B, effective stress at point B, okay, total stress minus pore pressure. So 201.806 kilopascal minus 19.62 kilopascal. The effective stress is 201.806 minus 19.62, 182.186 kilopascal. So that's the answer. And this is also the final answer, the effective stress for 10 meters below the surface. So that's how we solve a problem which involves capillary action on soils.